Today I will explain how to use my program for calculation of reflection and transmission for a multilayer structure, also called photonic 1D structure. Even the number of layers may be 1,000 or even 1,000,000. The program calculates the reflection and transmission nearly instantly. The calculations are fast and rigorous. It means that no assumption or simplification we use. The calculations are based on direct solution of Maxwell equation, which are optimized for a larger number of layers and fast calculations. As far as the Maxwell equations are valid and the used data of refractive index are correct, the data calculated by this program are absolutely precise. Therefore, it is ensured that there is no data divergence because of error accumulation due to use of large number of layers or complex structure or use of metal layers. Another merit of this program is that it is absolutely free with fully open code, so you can understand, modify and use the code in your program. I hope the program has a user-friendly interface. In previous video I already explained how to download and install the program. In short, you download zip file of program from my website here. If you don't have a LabVIEW to install on your computer, you need to download and install the LabVIEW driver, also called LabVIEW library from National Instrument or from my website here. Unzip the files into a directory of your choice and everything is ready. There are LabVIEW and executable files with the same name. They are identical. You can use either of them. There are 3 programs for calculation of waveguide mode, surface plasmon, and reflection transmission. Today I will explain only how to use the program for the calculation of the reflection and transmission. I will start LabVIEW file and you click here to start it. As an example, let us calculate a multilayer structure from this paper. I will show you how to calculate the transmission and reflection from this multilayer structure, also called 1D photonic crystal. As a first step, we define our structure, so go here to the right. In this simple case, the light incident from air and finally transmitted to air. So we keep the airs at the bottom and top layers. Later I will show you how to use a prism. Next, let us define our structure. At present, our structure has 2 layers, MgO and silicon dioxide. We can check thickness and refractive index of each layer just from here. For example, put 500 nanometers here or 300 nanometers here, or you can put different refractive index like this here. But the right way to change the layer structure is from separate window. Click here. These 2 layers, MgO and silicon dioxide, is shown also here. This is number of layers, and at present there are only 2 layers. We can change this number, for example, to 1, or increase it, for example, to 10. So you see 10, or to 100. Yes, like 100. When it is necessary to go quickly to a specific layer, just put number here. For example, 45. Yeah, just put 45. And it is a layer number 45. At present, all our layers are empty with refractive index equal to 1 and 0 thickness. Next, we will fill each layer with a material. There are several methods to do it. The first option is just download data from file. The second option is calculate from formula. And the third option to input it parametrically. The first option is to take data from file, like this. The directory for files from any material is named refractive index, and it can be found in the directory where you unzip your program. The files are the text files, therefore they can be opened by any text editor. For example, let us open the file for zinc oxide. I'm using Notepad++, but any text editor is okay. There are 3 columns of data. The first column is the wavelength in micrometers. The second column is the real part of the refractive index. And the third column is the imaginary part of the refractive index. You can prepare your own file for material you needed and copy it to that directory. You can find a ton of data of the refractive index in the website named Refractive Index Info. So let us load the data of some material from file, for example, zinc oxide. This graph shows the imaginary and real parts of the refractive index versus wavelengths. You can change the display wavelength range, for example, from 700 to 1000. Additionally, it's possible to use different units for imaginary parts of refractive index. Here you can check in, if you want to see, you can check in reverse centimeters or decibel per, say, micrometer, and so on. So let's back to the wider range. It's possible to compare the dielectric constant of several materials. For example, I will compare 3 materials. For this purpose, I will display 3 graphs simultaneously. So I put here number 3. Now it's only zinc oxide. Let us add some material. For example, ITO. Yeah, very popular material. Now zinc oxide is shown in red, and ITO as the last loaded material is shown in white. Next, I will add silicon. Now silicon is shown in white, ITO in red, and zinc oxide in green. So you can compare dielectric constant of different material for use in your application. If you don't want to see other material, put one here and you will see only data of refractive index for silicon. The refractive index is loaded from a file when the material dispersion is rather complex. When it is simple, for example in case of oxide, the refractive index can be calculated from formula here. You can choose your material, for example silicon, here, and push it and load it. That is for silicon. For the calculation, it does not matter where the data of the refractive index came from. It is only important that the data is correct. You can compare the data of the same material from different sources. Let us display two graphs. Here. And let us download silicon from the file. That is the silicon. You can see there is some tiny difference. And here, for example, from formula there is no silicon absorption in this region. And there is some spark here. The third option to download the refractive index is from material composition. For example, we can download the data for any composition of binary 3,5 compound. Choose this option 3,5 semiconductor. Choose the two material of your compound. For example, aluminum gallium arsenide, aluminum gallium arsenide. Then X is concentration of aluminum. So let us compare the dielectric constant for two concentrations. So push from parameter. Only one first. This is the dielectric constant for 0.4 concentration of aluminum, concentration 0.4. Next let's choose 0.1. Now 2 from parameter. So white is a correspond to 0.1. Since the band gap of these two concentrations are different, the refracting index and absorption coefficient are different as well. There are many choices here, so you can practically input data for any binary 3,5 semiconductor. Let us come back to our photonic crystal structure and input data of the refractive index for it. As you can see, there are many layers which is repeated periodically. Now I will show you how to input such a periodical structure. For example, if we have 7 nanometers zirconium oxide followed by 5 nanometer silicon dioxide, and it's repeated 7 times, how we should input it. So I take zirconium oxide from formula, here it is, push here. This is zirconium oxide refractive index. Here we see zirconium oxide. Here we see the name zirconium oxide and its zirconium oxide refractive index at this wavelength. Thickness now is 1000 nanometer. I change thickness to 7 nanometer. Next, we need to put zirconium oxide in many layers. The same data should be repeated in many layers with same pattern. This part put data of repeated pattern in our structure. This number means at which layer the repetition starts, and this number means after how many layers the layer is repeated. In our case, zirconium oxide repeats each second layer, so I put here 2 and here start bottom. I will start, for example, from 0, so 0 means the first layer, this layer. So next push set layers. So you can see now each second layer from beginning to the end is zirconium oxide with thickness 7 nanometer. Next, let us input silicon dioxide. So I choose silicon dioxide here. Okay, we can just compare. And from formula, So we can compare zirconium oxide and silicon oxide layers. Zirconium oxide is much higher, shown by red. And we see named silicon dioxide here. Silicon dioxide thickness is 5 nanometers, so I input it here. The zirconium oxide starts from layer number 0. We will start silicon oxide from layer number 1. Similarly to zirconium oxide, silicon dioxide layer repeats each second layer, so remain here 2. Push the set layer. You see now we have repeated zirconium oxide, silicon dioxide till the last hundreds for each 100 layers. Perhaps we don't need hundreds of layers. I will reduce to 14. So now much less, only 14 layers. And we can plot the distribution of refractive index and absorption coefficient in this window for this structure. For this, push this plot layer. Yeah, and again, we can reduce to 1. If we want to compare two structures, we can use 2. So now 1. And you see that is a 7th layer of repeated zirconium oxide have a higher refractive index, silicon dioxide smaller, and we have such a structure. It's going to 85 nanometers. Let us come back to our structure and input it exactly as it is. I will begin from the lower part until garnet. The lower part has 1 layer of substrate plus 14th layer of periodic layers. In total, the lower part, this part, has 15 layers. Let us reset the layer structure. For this purpose, input the number of layers 1. Yeah, so whole structure disappears. Only 1 layer remains. Next, input 15 as the number of layers of lower part. Yeah, we have empty materials here. First, we input the substrate, which is a glass. For this purpose, with a glass refractive index here from formula. Substrate has no repetition, so put 0, meaning no repetition, and substrate starts as the first layer from the bottom, so its number is 0. And click set layer. You can see glass is only in the first 0 layer. Next, I need to input 14th layers of these multilayer structures on top of substrate. Next layer after substrate is zirconium oxide. So I choose zirconium oxide from the formula. Zirconium oxide. Input its thickness of 7 nanometers. And zirconium oxide repeated each second layer. So for repetition or periodicity, I put 2 here. So means I repeated each second layer. So next I need to set its first number. So 0 number is occupied by substrate. So next available number is number 1. 0, 1. So I input 1 here and click set layer. So now each second layer after substrate is zirconium oxide. on top of zirconium oxide there is always silicon dioxide, and with sample repetition of 2, so it's silicon dioxide also each second layer. So I download silicon dioxide from formula, input its thickness of 5 nanometers. Number 2, repetition number is remain 2, but starting number is this one, 2. So first is the zirconium oxide. Now we need the second layer, so I input 2 and click the set layer. So now we have a repetition of zirconium oxide and silicon dioxide layers. So far we input data up to the garnet. So let's next input the garnet on the top of last silicon dioxide layer. For this purpose, first, we want to input garnet here, so we need to increase number of layers by 1 till 16. Next, we load garnet data from file. So with music, for example, several files, we can choose this one. From file. And next we input the thickness of garnet, which is 800 nanometers. And we need input only the garnet film is only single, so we don't need any repetition. So we put 0 as repetition number, and we need to put garnet in this cell for this layer. As you see, it's number 15. Because it's layer numbering starting from 0 in LabVIEW, so we have total 16 layers, and this layer number is 15, so we input 15 here. So we have a garnet here. On the top of the garnet we have more 14 layers of zirconium oxide, silicon oxide multilayer. Again, we need to increase number of layer by 14, so 16 plus 14 in total 30 layers. So next layer says silicon dioxide, so let's load it from formula. Silicon dioxide, it put in its thickness of 5, and we need to put silicon dioxide right after the garnet. So garnet is layer number 15, and next layer is layer number 16. So I put 16 here, and silicon dioxide repeated each second layer. So as repetition number I put 2, and I click set layer. You see, after garnet, each second material is silicon dioxide. Next, on top of silicon dioxide, I need to input zirconium oxide with the same repetition number, because it's zirconium oxide repeated each second layer. So I load zirconium oxide from formula, input its thickness 7, and we need to put zirconium oxide here just after silicon dioxide, and its material 17, so we can double check it if we move to left corner, so it shows a 17. So we put this here 17, and repetition number is 2, and we click set layer. So you see now we have a repeated structure of silicon oxide, zirconium oxide till the end, starting from garnet. Now when we set our final structure, we can check it, how the refractive index is distributed over the thickness. For this purpose, we just need to click plot the layer, and this is our structure. We can still modify, for example, we can slightly reduce substrate thickness and replot it. Also we can choose number of layer which will be shown. So it's at 2 now, so we can reduce to 1, and we can see our result. Distribution of refractive index. So we finish inputting all layers of this structure. So now we can just simply click set layers, and our structure is loaded for calculations. But before doing calculations, I want to show you some other parameters and their functions for inputting the data. I can save the structure if I plan to use it in future. For this purpose, I click Save Layer, give some name. Yeah, I'll just try. For example, most close zirconium oxide, silicon oxide, garnet, B2, some unique name. You save. Next, after you reset your structure, so put 1 here, so everything disappear. You can load this structure, which is B2, so everything appear again. Now I have finished with the input of the structure. I hope it is relatively easy and simple to do. Next, click Set Layer and go to the main window of the program. You see our structure is loaded here. The distribution of refractive index also displayed here. Additionally, we can compare distribution of different structure or the same structure different parameters here. For example, let's display 2 graph. So put 2 here, and let us change wavelengths and see how distribution of the refractive index changed. So put like 800 here. You see white one is for 800 and red one is for 1.5 micrometers. So let's come back to nanometers, and let's display only 1 layer. Before I will show you how to do calculations, I would like to show you some additional options for input of the structure. So let's come back. Our structure, which is here, will be displayed in our input window. This part describes parametric input. It is for the case, for example, when you have some compound material and concentration of your compound change with thickness with some known function, for example Gaussian or error function. Such distribution you can input parametrically in this part. However, details about how to do it I will explain in another tutorial. This part is responsible for wavelength dispersion. You see, we input here what we see, it's just refractive index at this wavelength. But if later on you're planning to calculate some dependency on wavelengths, you should transfer to calculation program some data about how the refractive index changes with wavelengths. And that is a range which you're transforming, and that is a number of points. So just input your wavelength range within which you're planning to do calculation, and you can input here a reasonably high number of points if you have a good computer. That is all about methods how to input refractive index for multilayer structure for our program. So let's close this window and go to main calculation program by clicking Set Layer.